Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello, welcome to Physics with Beth and Beth. I'm Beth, and we are on AP Physics 1 still, but you're doing great. We only have 2 more units after this. Hang in there, you're almost there. And it's about energy and momentum in rotating systems. Okay, we're just going to jump right in. The last video we just posted was about this universal potential energy and what we define as the reference point and how it's different from when we look at potential energy on Earth. Well, in this problem, we're actually going to work with this universal potential energy. So we have a rocket that takes off at 5.0 kilometers per second from a launch pad, and they want to know what altitude will it reach before falling back to Earth. Okay, you're not given a lot of information. In fact, you're really only given one thing here. So we're going to figure out how to do this problem. So let's just get started, shall we? Let's take off on this problem. So here we go, pun intended. We're going to use mechanical energy on this. Okay, we have mechanical energy before is going to equal mechanical energy final. I've drawn a little Earth. Now you all know my colleague Beth is the artist of the group. She's also the one who hand designs our t-shirts that you can find the link on our YouTube channel. But she's the artist, I am not, so please bear with me on these terrible pictures. But I have the Earth here, and I have a rocket setting on the launch pad. And then this is before, and then after, I have a rocket that's at some max height. And spoiler alert, it comes back down to Earth. It does not hit its escape velocity or its escape distance and to fall back, and it falls back to Earth. So spoiler alert. So we're going to work on this problem. All right, I've given you some constants that we already know, that G is 6.67 times 10 to the 11 times 10 to the negative 11. The radius of the Earth is 6.38 times 10 to the 6 meters, and your mass of Earth is 5.98 times 10 to the 24th kilograms. All right, we're going to get started. So now before, and we'll review this, it was also in the last video, but before, when we were talking about an object up in the air on Earth, we would do the potential energy gravity as mass times little g times the height. If we had this little roller coaster and it went like this, and we had a roller coaster up here and it was at rest, we're going to ignore friction, there's no friction, and then it comes down here to the bottom. We would say, hey, this was all potential energy, which is mgh, and it all gets turned into kinetic. And our mechanical energy before and final would look like potential energy going to kinetic, as long as we assume there's no friction. All right, because we put the reference point here on the ground for potential energy on Earth. And we're dealing with not masses out in the universe on here. We're dealing with a very small area and only the effects that Earth has on this cart. That's why we use mgh, or mass times little g times height, for potential energy when we're dealing with these little objects, a free fall, a ball thrown up in the air, those kind of things. Because again, dealing with a small little area, dealing with the effects of Earth on that object, not all the masses in the universe. Well, for universal potential energy, it's different. For universal potential energy, we are addressing all the different masses that are out in the universe, all right, and how they interact. So we're going to go ahead and do this. This is getting way off our planet here. So not enough to go into orbit around us, but way off our planet. And we're going to be using this universal potential energy. So we're going to look at the first. Now I know it's setting here on the launch pad, but it gets up to 5 kilometers. This rocket's going to take off, I should say, at 5 kilometers per second. So we're going to do it right after it's left the Earth. It's not touching the surface anymore, but it's at that 5 kilometers per second. So we're going to say that's got kinetic energy, because now the velocity is 5 kilometers per second. I'm going to go ahead and write that here, and actually that's 5,000 meters per second. All right, now there is a universal potential energy here as it's moving. All right, and that I like to call that UG, just so we can remember that's universal versus our mgh for our other one when we're talking about just on Earth. And that's going to be the initial. All right, then we're going to have for final, it's going to stop. It's going to be at max height before it falls down. So its velocity is going to be 0 up here. And that means no kinetic energy, but you definitely still have this universal potential energy final, we're going to call it. Okay? All right, now I'm going to start filling in our variables for these things. We're going to remember that kinetic energy is 1/2 mv squared, mass times velocity squared. And we're talking about the rocket here. The rocket's the one that's moving, so R for rocket. All right, that's kinetic energy. We're going to remember that our universal gravity, the UG, the universal potential energy, I should say, is negative big G mass, the two masses you're dealing with, which here's the rocket and Earth, over R. And remember, this R is the distance from center of mass to center of mass of both objects. Okay, perfect. Now, again, people are like, why is potential energy negative? It's never negative when we're dealing with that little MGH formula, all right, on Earth. Okay, why? Because we use on Earth the ground as 0 reference point. So if you're above the ground, you have positive potential energy. All right, but in the universe, we have defined the reference point as an infinite distance from us. So that means that we're on this side of that reference point. So we are in negative. And why? And you're like, I don't even understand why they did that. Well, because the closer two objects get in space, the more bound they are together because of this force due to gravity, this universal force due to gravity, and the more energy it's going to take to break them apart. All right, so potential energy then is negative, and it's going to get more negative the smaller this distance becomes between them. Hopefully that helps you understand that. If not, just remember Toy Story, to infinity and beyond. All right, we've defined potential energy in the universe, universal potential energy, as an infinite distance. And we're not there and we're not beyond it. We're not at infinity or beyond, so it's not 0 or positive, it's negative on this side. All right, hopefully that'll help. All right, so let's go put on our variables. We have 1/2. We said, hey, it's the rocket that's moving, Earth is moving too, but if we're looking at the rocket moving off the Earth, we're looking at that rocket moving. So that's 1/2 mv squared of that rocket initial, plus a negative big G, mass of the rocket, mass of the Earth, over that distance from center of mass to center of mass. So let's look at this. Let me draw that picture out for you. That's going to be right here is my center of mass for the Earth, and here's my center of mass for the rocket. So guess what? It's going to be the radius of the Earth. All right, it may be a little off. Not enough in this problem with these huge numbers to matter if this rocket were just a little bit off with center of mass, but it's going to be radius of the Earth. It's going to be close enough considering all these big numbers we're using. Then we're going to go to our final potential, universal potential energy, and we said, hey, this rocket's at 0 because it's hit max height and it's coming back down. Spoiler alert, it crashes back down, it doesn't make it. So we're at negative G, mass of the rocket again, mass of Earth, over our final. And what's our final here? Well, let's look at that. Our final is from center of mass of one object to center of mass of the other object. All right, so that's going to give us our final distance from center of mass to center of mass. Perfect. Okay, now we can start looking at this. I want altitude. We have to define what altitude is. Here's what altitude is. Altitude is defined as the height above the surface of the Earth. I'm going to write that up here, that altitude is defined as the height above the surface of the Earth. Okay, well, right there, let me kind of put these over here in a box. Surface of the Earth. Okay, you're like, oh, okay, but wait a minute. Our final that I'm going to be finding is distance from center of mass to center of mass. Okay, that is not from the center, from the surface of the Earth. That's from the center of the Earth. So guess what? If I have my RF and I subtract the Earth's radius, look what I have. I have the height above the Earth. I have altitude. So I'm going to draw that out here. So this is what I'm looking for. I'm looking for this distance above the surface of the Earth. That's altitude. Okay, well that's going to be RF minus radius of the Earth gives you altitude. So I'm going to write that. I'm going to say the altitude is going to equal that final R, distance we're looking at, whoopsies, minus the radius of the Earth. All right, we're going to remember that little handy dandy formula right there when we get to the end. Okay, now we are simply, oh, first of all, look, everybody brought mass of the rocket up to the party. Woohoo! Classroom, I'd be playing Party in the USA. We'd all be having a little dance break because everybody brought mass of the rocket to the party. I'm going to now clear this up. That's 1/2 that V naught squared minus, I'll just put minus G, mass of the Earth over the radius of the Earth. We now know that's the radius of the Earth. Minus G, mass of the Earth over R final. Okay. All right, we're going to put numbers in for that. And we're going to solve for this R final, that distance between center of mass of the Earth to center of mass of the rocket at its max height. So that's going to be 1/2. That's going to be 5,000 squared minus 6.67 times 10 to the negative 11 over 5.98 times 10 to the 24th over the radius of the Earth, which is 6.38 times 10 to the 6th. That's going to equal a negative 6.67 times 10 to the negative 11 times the mass of the Earth again, which is 5.98 times 10 to the 24th over RF, which I'm looking for. Now, if you do that math, your final R is going to end up being 7.9, is that right? Yeah, 744 times 10 to the 6th meters. Okay. Once you get your head wrapped around this universal potential energy, then this problem is not really that difficult. What is difficult is plugging all of this junk into your calculator, quite frankly. All right, my suggestion to you, and it's always been my suggestion to students, if you're using a TI-84, use that double E button. It really reduces your chances of error. How it works is, you'll see it on a second function, listed. It's a second function, so hit that second button and then find the double E and hit it. But here's how you do it. Like if I want to type in 6.67 times 10 to the negative 11, I would type in 6.67. I would just hit the double E button. No times, no divide, no nothing, no caret to the exponent, nothing. Just 6.67, then hit that double E button, and then just type in your exponent, which here is negative 11. And then I would have hit a times, and then I would do 5.98, hit the double E button again, and put in 24. All right, practice with that, and then I would hit divide, and I would do 6.38, double E button, and then 6. So you don't have to do the double E, literally represents times 10. That's what the double E button represents. It's way easier, I think anyway, personally. It definitely helps reduce errors. Once my students figured out that, they were not having as many errors with trying to calculate these huge numbers. All right, so just a helpful hand. Now, I have our final. We said that's not what the problem asked for. The problem asked for altitude. So I'm going to go ahead and I'm going to erase this now that we understand that. And I'm going to go ahead and put in that, hey, my altitude is equal to that 7.9744 times 10 to the 6th minus the radius of the Earth, 6.38 times 10 to the 6th. And I get an altitude of 1.59 times 10 to the 6 meters. And that's appropriate because a rocket can go up to 2 times 10 to the 6th, actually meters, before it's out in space. So that makes sense that it fell back down depending on speed. But anyway, there you go. That is how you do this problem. If you like this video, please give us a thumbs up. If you haven't subscribed, we would love for you to do that. If If you have some peers that are struggling in physics and you think these videos are helping, we would love for you to share our YouTube channel with them so we can get word out and we can help others. That's why we're doing this, to help you all. And thank you for watching, and happy physicsing.